Koteswaramma, Assistant Professor of EC Department from Institute of Aeronautical Engineering, Hyderabad. Today I would like to discuss about magnetic flux density, and then we will derive one Maxwell's equation from magnetic flux density. That we will see now. So if you go for magnetic flux density, that is represented with the symbol capital B. If you go for electric field, electric flux density is represented with capital D, but whereas magnetic flux density is represented with capital B. And this is similar to D in case of electric field. If you take D relation in case of electric field is given as D is epsilon naught into E. If the medium is a free space, then electric flux density D will be given as epsilon naught into E, where epsilon naught is permittivity of free space and E is electric field strength. Similarly here, if you go for magnetic flux density B, that is related to permeability of free space, which is given as mu naught, and magnetic field strength as H. And this magnetic flux density is linked with mu naught and H, as B will be given as mu naught into H. B is magnetic flux density, that is the product of permeability of free space and magnetic field strength. So here mu naught we can call as permeability of free space. Its value is constant, which is 4 pi into 10 to the power of minus 7, and units for this mu naught are Henry per meter. And if you take magnetic flux lines representation is always from north pole towards left pole. If you take electric flux lines always starts on the positive charge and the ends on negative charge. Similarly here magnetic flux line starts on north pole and the ends on south pole. And magnetic flux density and magnetic flux relation is given as magnetic flux psi is equal to integral of B dot ds. Or if you take magnetic flux density B, that will be given as flux per unit. Here this is B. This B is flux per unit area. And to get flux value, we have to multiply B with ds, and to get the total value, total flux, we have to integrate that one. That is given as equation 1. Flux is linked with flux density as flux equal to closed integral B dot ds. That integration is over a surface. And here if you go for the units of flux, magnetic flux is given in Webers. And magnetic flux density is Webers per meter square, or you can call it as Teslas. So the units of magnetic flux density are Webers per meter square or Teslas. And if you take magnetic flux, here magnetic flux lines always starts on north pole and ends on south pole, I told you already, and always it requires a closed surface. But whereas if you go for electric flux lines, they don't require a closed surface. So as electric flux lines are not taking a closed surface, if you take electric flux lines, its relation is closed integral D dot ds equal to Q. But whereas in magnetic flux lines requires a closed path always, and that will be given as closed integral B dot ds equals to 0. And what we can say here is an isolated magnetic charge does not exist. That means if you cut a magnet into smaller pieces also, then it always has both south and north poles. And the total flux through any closed surface in a magnetic flux will be 0. So here, if you observe the relation closed integral B dot ds equal to 0, here magnetostatic field is not conservative, but magnetic flux is conservative. What it means is, if you take magnetostatic field, closed integral H dot dl is not 0. Closed integral H dot dl is always equals to J. So from that what we can say is magnetostatic field is not conservative. But if you go for electrostatic field, closed integral E dot dl equal to 0. That says the electrostatic field is conservative. But here magnetostatic field is not conservative, but magnetic flux is conservative. As magnetic flux is conservative, closed integral B dot ds equals to 0. now if you take magnetic flux relation, which is closed integral B dot ds over a surface, which is equal to 0, and now I am trying to apply divergence theorem to that equation. What divergence theorem says is, divergence theorem gives the relation between surface integral and volume integral. So now here, if you apply divergence theorem to closed integral B dot ds to this term, then that will be written as del dot B into d. So now from this equation, this entire product must become 0. But dv never becomes 0, then the other term in the product must be 0. Then from that del dot B equal to 0. This del dot B equal to 0 is given as fourth Maxwell's equation. So fourth Maxwell's equation is obtained from magnetic flux density term, which is represented as B. And that fourth Maxwell's equation is del dot B equals to 0. And another point we can say under magnetic flux is magnetostatic field is not conservative, but magnetic flux is conservative. And one more point is magnetic flux lines always starts on north pole and they ends on south pole, and always it requires a closed path. This is about magnetic flux density and Maxwell's equation. So this magnetic flux density gives us the fourth Maxwell's equation. So now here I am going to conclude this Maxwell's equations for static EM fields, or I am going to describe all the four. I am going to give the summary of Maxwell's equations for static fields. If you observe Maxwell's equations for static fields, we have two Maxwell's equations for electrostatic fields and two more equations for magnetostatic fields. And if you take two Maxwell's equations for electrostatic fields, in that first one is del dot D equals to rho. That is obtained from Gauss law. So del dot D equals to rho V, which is the first Maxwell's equation in differential form. And the same in integral form is closed integral D dot ds equals to closed in here volume integral rho V d, and that is due to Gauss law. And the second Maxwell's equation for electrostatic field is del cross E will be given as 0, which is differential form, or we can call that one as point form, which is equals to closed integral E dot dl equals to 0. Now the integration is over line, and that is obtained due to the fact conservative nature of electrostatic fields. As electrostatic fields are conservative, closed integral E dot dl equals to 0. These are two Maxwell's equations for electrostatic fields. And if we take Maxwell's equations for magnetostatic fields, in that first Maxwell's equation for magnetostatic field, or that we can take as third Maxwell's equation, is del cross H equals to J, which is obtained from Ampere's law. Del cross H equals to J is the representation of Ampere's law in differential form. And if we can take the same one in integral form, closed integral H dot dl over a line equal to J dot ds over the surface. And the fourth Maxwell's equation, or the second Maxwell's equation for magnetostatic field, is del dot B will be given as 0. Del dot B equal to 0. That is due to the fact non-existence of magnetic monopoles. That means there is no north or south poles isolatedly. The combination of both north and south poles only existed always, and that the same equation in integral form is given as closed integral B dot ds equals to 0 over a closed surface. This is about Maxwell's equations for static EM fields. 2 for static electric field, 2 for static magnetic field. Then by combining those, we have 4 Maxwell's equations for static EM fields. This is about magnetic flux density and Maxwell's equations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.